Hello, welcome to this video. In this video, we will learn first law of thermodynamics for an open system, or we also call it as steady flow energy equation. Now, what is an open system? Let us understand an open system. An open system is a system where both mass and energy can cross the system boundary. So, here we can see that there is a open system example here. Mass is coming in and mass is also going out. Unlike a closed system where mass is fixed. Here, both mass as well as energy can cross the system boundary. If you see, most of our engineering devices are open systems. So, for example, a turbine. So, turbine, you have a high pressure, high temperature steam coming in and low pressure, low temperature steam going out. So, it is a mass coming in and mass going out example. Similarly, compressor, where air comes at lower pressure and leaves at higher pressure. Pump, water comes at lower pressure, leaves at higher pressure, and so on. So, you have nozzle, diffuser, and heat exchanger. So, where mass and energy both can come in and go out of the system boundary. So, now we call this as a control volume, where our attention is concentrated. Now, in order to talk about an open system, we know that the first law of thermodynamics is all about law of conservation of energy. What law of conservation of energy states? Energy can neither be created nor be destroyed, but it can be transferred from one form to the other. So, energy coming in should be equal to energy going out, or if energy coming in if is not equal to energy going out, it should be change in energy of the system. So, if there is some energy coming in and some energy going out, you can see that this is 100, but if this is 100 kilojoule, let us say, and this is only 50 kilojoule, where is that remaining energy has gone? That would have resulted in change in energy. Remaining 50 kilojoules has gone here. That is what we have written. For example, in this example, 100 minus 50 is equal to 50 kilojoules. So, that is the energy change of the system. Now, let us talk about steady flow energy equation. So, if we talk about steady flow energy equation, the device which we are considering is steady. Steady means the properties remain constant with respect to time. For example, mass flow rate is constant. If there is 10 kg per second happening now, after 10 minutes also it should be 10 kg per second. And obviously for a steady flow device, whatever coming in should be going out. So 10 kg per second is entering means it is going out. It is not a storage. Mass is not being stored in the system. Now, properties at inlet and exit do not change with respect to time. For example, velocity here may be 50 meter per second, velocity at inlet. Velocity at outlet may be 20 meter per second. What we are saying, velocity can change with respect to space, but with respect to time, for example, after 10 minutes, 20 minutes, velocity at inlet remains same. That is why we are calling it as steady flow. The properties do not change with respect to time. So, at inlet and exit, they do not change with respect to time. And system operates continuously. It is not an intermittent flow kind of a device. It is a device which operates continuously. Okay. With that note, we will move on to derive steady flow energy equation. Now, we have considered a steady flow device. What is a steady flow device? Out of any example which you have taken, let us say compressor. Compressor must have an inlet. Compressor must have an outlet where mass is going out. Okay, and let us say this is kept from certain distance from the floor. Okay, so mass is coming in here, so mass is coming in here and mass is going out here. Let us consider a section here and call this as section 1, section 1 and at the outlet let us call this as section 2. Okay, now we can also say the distance from here to here, the distance from here to here and here to here, that is from ground, we call this as Z1, the height Z1, and this as Z2. Okay. Now, let us go back to our equation. Energy coming in must be equal to energy going out. Energy coming in minus R, we'll call it as energy coming in is equal to energy going out. Let us come back to that equation a little later. Energy coming in must be equal to energy going out. So, if we balance this, obviously we will get what is the change in energy of the system later. So, what is the energy coming in? Let us assume a positive heat transfer. So, positive heat transfer is heat given to the system is positive. So, let us say that heat is given to the system. Let us say this system receives heat. Let us call this as Q. System receives heat, that's why it is positive. And similarly, let us say that this is a device which gives you work output just to keep these things positive. Okay. Now let us go back to this equation. Energy in is Q and must be equal to energy going out, that must be W. Now remember, these are not the only two forms of energy which is crossing the system boundary. There is energy associated with the mass coming in and mass going out also. So let us try to take that also into consideration. What are the energies which are associated with the mass? So there could be a temperature of the coming fluid. Let us say the temperature of the fluid which is coming in may be 100 degrees Celsius. So it must have a internal energy. So I will say specific internal energy for now, and we'll call it as U1. And on the other side, it must be living with some internal energy. Let us say that is U2. At some temperature, we'll call it as U2. And then it may also have flow work or flow energy, the energy required to cause the flow work, which is given by P1 and V1. Specific volume I have written. So this unit will derive P1, V1. And then it may also have kinetic energy. So we are writing it for unit mass. So half V square only. So V1 square. At section 1, we are writing V1 square. So this side we will have flow energy V2 plus half into V2 square. Remember, there are two V's here. One is small v, which is specific volume, and this capital V is velocity at inlet and outlet. And lastly, we have potential energy. The energy equation, the potential energy is given by mgh, or we are giving it a name Z. So G Z1. So this was equal to W here. Okay. Outlet also we can write it as G Z2. Now let us rewrite this in a famous form which we know, Q minus W. So Q minus W is equal to, I will send all these other terms to the right hand side. You will have U2 this side plus P2 V2 there only, and this goes here minus U1 plus P1 V1 plus this half into V2 square is here minus half into V1 square comes from the left side plus G into Z2 minus G into Z1. Remember, we have written it for unit mass. That is why we have neglected M here, half into mv square or half mgz or mgz. Okay. Now let us rewrite this Q minus W. Now what is this U plus PV? From definition we know specific enthalpy is given by U plus PV. Now U plus PV H2 minus U1 plus P1 H1 plus half into the velocity of the fluid which is coming in V2 square minus this V1 square plus G into Z2 minus Z1. Okay. Let us try to derive what we are trying to write here. The units. H2 should be in joule per kg. Then V2 should be in meter square per second because velocity is in meter per second. So this should be in meter square per second square, but we'll know that that is same as this. Now G into Z, this also should be joule per kg. And the moment the right hand side is in joule per kg, Q and W should also be in joule per kg. We'll prove that meter square per second square is also joule per kg later. Now in its simplest form, what we can write is Q minus W is equal to change in enthalpy plus change in kinetic energy plus change in potential energy. So this is what we can write in its simplest form. Alright. So we can also write the differential form here also, delta Q minus delta W. Now if you would like to represent this in with respect to like mass flow rate, for example rate of heat transfer, then let us say Q dot. Now this is in joule per second watt. Okay, minus W dot. Again the same equation I am rewriting. This is our equation 1. Equation 1 I am rewriting. Rewrite equation 1. Now equation 1 I am writing it with respect to time. The equation 1 was SFEE, that is steady flow energy equation with respect to unit mass. Now what we are deriving is with respect to unit time. Okay. So this is one equation and what we are writing is another equation with respect to time. Okay. So is equal to mass flow rate into H2 minus H1 plus mass flow rate into half into V2 square minus V1 square plus mass flow rate into Z2 minus Z1. Okay, call this as equation 2. Equation 1 and equation 2 are same, just that it is represented in unit time and unit mass. So if this is in joule per second and mass flow rate should be in kg per second, and this you know that enthalpy you are representing it in joule per kg. So this kg goes up, joule per second, that is watt. So here also you have mass flow rate in kg per second and this velocity square will give you joule per kg. We will derive that. Kg per second goes off, joule per second, again here kg, and G into Z will give you joule per kg. This also goes with kg and you will have joule per second equal, which is watt. Now we will prove that y joule per kg and joule per kg is also equal to velocity square, which is meter square per second square. Now joule is what? Newton meter kg. Okay. Now Newton meter can be further written as kg meter per second square. So that meter is there only, and this is kg meter per second is just Newton. Okay, meter is there, kg is there. So kg goes off, you will have meter square per second square. So that is what we said, velocity, if you substitute in velocity in meter per second, you will have meter square per second square, which is nothing but joule per kg. So meter square per second square. Similarly here, acceleration due to gravity is meter per second square. This is the unit of g, and z should be in meters. So this will give you meter square per second square. Okay. So if you write what all these quantities, for example, P1 is pressure at inlet and similar is P2, pressure at inlet. Now what were there? U, V1, specific volume, specific volume meter cube per kg. So specific volume meter. So we'll write just PV. So inlet and outlet we already know. So P is pressure at inlet, V is specific volume. Pressure should be in Newton per meter square. Volume is specific volume which is in meter cube per kg. Now U is internal energy in joule per kg. Internal energy in joule per kg unit should be carefully written. Then capital V is velocity in meter per second. G is acceleration due to gravity. Acceleration due to gravity. And that we know 9.81 meter per second square. So Z is height from reference point. So inlet and outlet we can always write. So we know that there are two forms of steady flow energy equation. Our first law of thermodynamics for an open system. One is with respect to unit mass. So everything should be in joule per kg. If you want to rewrite the same equation with respect to time, it should be watt on both sides, that is joule per second. So right hand side will be multiplied with mass flow rate, and left hand side if you have joule per kg you multiply it with mass flow rate, or if you have watt, that is fine, straight away you can substitute watt is equal to m dot into these properties. Thank you.